Hi, welcome to Boulder City, Nevada. I'm Doug Smith, and I have a little bit of a smoke and flame and spark experiment for you here. More spark, actually, but it's one of these things that are pretty interesting. So let me show you what I got for you. I've got a new way of making some high voltage pulses here to test resistors. So what I have is a neon sign power supply. Now these things aren't just transformers like they used to be back in the 50s. It's actually a switching supply, puts out 10,000 volts RMS, 32 kilohertz out of the output. Although it turns out if it doesn't detect the neon sign out there, if it doesn't see current, it turns off in 150 milliseconds or something. So it's actually a safety feature, I guess. But I'm going to use this. I'm coming through, here's a little neon bulb we'll see blink when we charge things up. Underneath the tape here is several 30 kilovolt rectifier diodes. Then there's a little spark gap, and under the table is this big capacitor. I think I showed in a previous video. It's about, it must be 40-50 pounds. It's very difficult to lift. 15,000 picofarad, 50 kilovolts. But these diodes, through a little gap here, charge the capacitor up to about 15,000 volts peak. And the purpose of the little gap there, which I just got a little thing, there was a little charge left in that thing. Got to be careful with these things. Once the capacitor charges up, the little gap opens up, and then when this doesn't see a load anymore, this thing turns off in 150 milliseconds. Safety thing. Let's discharge this. Well, it is pretty good there. Good thing I'm not grounded. But so we're going to use this to zap resistors. I make a point. I'm on a wooden floor here, and on a carpet on the wooden floor, and I'm sitting in a chair. Nothing is grounded. I always make sure I'm doing that when I'm with working with high voltage. So what I did here is I just charged up my little 150 picofarads of capacitance, and if I had touched something else, I would have discharged it, pretty much like an ESD vent. What would be bad is to get between here and here, which I'm very careful not to do. Okay, so we have these resistors. To give you an idea of how this works, here's an oscilloscope probe, a 10x high Z probe. It's about a 4 picofarad input capacitance. So it's just sitting here about that far from the high voltage lead. I want to show you what happens when I turn on the power supply. There we go. There's the power supply. There's the scope thing. So now I'm going to turn on the power supply and turn it off again. Now that capacitor, by the way, back of me is charged. So this screen factor here is 100 volts per division at 10 milliseconds. So this is reaching 200 volts peak into that probe's high impedance from 6 inches away. Let me expand that so you can see. Notice, by the way, that it cut off after some period of time. So we're 10 milliseconds, so 10, 20, 30, 40, 50, 60, 70, 80, 900, maybe a little more milliseconds. If I expand that, there's our 32 kilohertz. So that's what it does, and I sort of like the fact that it turns itself off after 100, 150 milliseconds or so, but sort of a safety thing. And while we're on the way back, you may have seen this in another video, we're going to compare some carbon comp resistors with some film resistors. These are sort of rugged. These are not as rugged. Some are called flame proof. Then there's wire on which we're not going to look at today, but they're obviously very rugged. Getting back over to here. Now, if you remember, I charged this thing up, so maybe it'd be a good idea for me to discharge it before I start working with it. There we go. You probably didn't see the spark because at 30 frames per second we might have missed it, but I'm sure you heard it. So let's get the ohm meter out here. Now we're charged to higher voltage than I did before. I think when I've been using this before, I was using my ESD gun, I would charge up to 7,000 volts, 10,000 volts, so forth. Now we're up at 15, which is pretty high. So let's get the ohm meter here. You can see that. So this is a carbon comp resistor, 2 watts, 50.3 ohms. I don't have 101 of those, although I would use it. Here's a 2 watt 100 ohm resistor, and this is running 100.4 ohms. And this one, we're only going to use one of them, but this one I think a little less, maybe 99.9 ohms. Being 100 ohms, it'll actually have a lower peak dissipation. The peak power here would be E squared over R, so this will, even though these are both 2 watt resistors, the film resistor will actually dissipate half the peak power. I just don't have a 50 ohm film resistor or a 100 ohm carbon comp resistor handy, so I'll use these two. Now we'll get the scope probe out of here so I don't burn anything up. Again, double check. Good. So here we have a few 30 kilovolt diodes, a little spark gap, and then the capacitor. It jumps the spark gap to charge it. Then the spark gap extinguishes as the capacitor becomes charged, and that turns this off. And now the capacitor is sitting there charged but not leaking back to the diode since I don't know what their leakage current is. So I forget there was 2 or 3 diodes underneath the tape here. Spark gap, capacitor. Okay, so we know these are pretty close, they're within tolerance. So I'm going to take this one here. There's 100.3 ohms, I recall. 101 would be the tolerance limit, 1%. Just put it there. I don't know if you probably can't see that NE2 neon light bulb, but it's going to blink. Now the capacitor is charged, and now we're going to discharge it through this resistor. Did you see the zap in the middle of the resistor there? It actually blew a piece of paint off the resistor. Well, E squared, 10,000 10 to the 8th ohms, maybe 2 times 10 to the 8th divided by megaohm, 1,000 watt peak power. So now let's go back over here. So you'd expect bad things to happen. Actually you would, but we'll see when they don't happen. So here we're back here again, and now we are 108.8 ohms. And the more I do this, probably the higher this is going to get. But we're way out of tolerance. Almost 109 ohms on a 1% resistor. So this one's shot. Let's try this one. This is sort of fun. I like playing with zaps like this. But again, I'm always making sure that I'm never in a position to be grounded with anything. There we go. It's charged up now. We might even do it again. And now we zap it. And now we measure it. Should probably get a little closer there. But let's see. Yeah, we can see the ohmmeter at the same time. So let's do this. 50.2, 50.3 really hasn't changed much, if any, within the tolerance. So let's do it again. We're charged. Try it again. 50.1. Now 50.2, this thing's plus or minus 1 digit, so there's no difference between 50.1 and 50.3 potentially. But anyway, it's not changing much. Let's do it a couple more times, and then we'll see if anything's really happening over time with this little thing. This is a lot of fun, by the way. And you can see the ohmmeter at the same time. 50.1. Let's do it one more time. And here we go. .1. So it hasn't changed. Back up here, and we'll get it so the window doesn't make things very quiet. So we see that the film resistor was out of tolerance on the first zap, and eventually it'll go completely bad. And this carbon comp resistor, we zapped it 4 times. It hasn't changed at all. It's within 1/10 of an ohm or where we started. It's still within tolerance. Very robust. But all of the resistors I talked about, the wire wound, the carbon comp, the film resistors, all of these can be dangerous in your system. And anything over a watt can be dangerous, even if it's not in a fault condition, even if it's operating normally. It can cause big problems in your system. It can cause fires, cause the system to quit operating after a few months in the field. So I developed a set of guidelines for components that are dissipating more than a watt. Whether or not they can take what's going on doesn't matter. If they're dissipating something like a watt or more, it's dangerous under certain conditions in your system. So I've got a set of design guidelines that I've come up with, and give me a call if you'd like to see those, or any other part of electrical engineering that you might need some help with. And maybe sometime come out here to Boulder State. It's only 110 today, I think, 108, 110, something like that, going up to 113 in another day or so. Perfect running weather. I'm going to go out and run 4 or 5 miles this afternoon. Okay, have a good time, and hope you enjoyed the video, and get it turned off here.